Welcome to the exciting course on real-time systems. So I'm Professor Smruti Sarangi from IIT Delhi. So I'll be presenting the slides made by Professor Rajib from IIT Kharagpur. So these slides come along with his book. So this is a slightly older version of his book, but we will be following a recent reprint. So his book is titled Real-Time Systems, as you can see, by Rajib Mal. The publisher is Pearson. So the plan of the course is like this, that we will spend some time on introduction, then discuss task scheduling. So I will go with the pronunciation scheduling and not use scheduling. And it's because this is something that this is a pronunciation that the audience from the Indian subcontinent is used to. So we will discuss scheduling, which is the key technique in real-time systems for uniprocessors as well as multiprocessors. After that, we will move to commercial real-time operating systems and discuss their pros and cons and their features. Subsequently, we will discuss some advanced topics, which is real-time networking, real-time communication, and real-time database systems. So we will also borrow some concepts from other classic real-time systems books by Jane Liu and Shin Krishna. So let's begin with the introduction. So the term embedded systems is something that we will hear quite often in this course. So this is basically nothing but a computer system that is embedded in some real world application. So there's a difference between real world and real time. So we will discuss this several times in the course of this lecture. Real world means embedded with something that is a physical system which affects human life. And real time is something in which the actual wall clock time actually matters. So, a lot of applications it doesn't, but in this case, it matters. So, according to a recent estimate, the number of processors that includes everything from microcontrollers to IoT processors to everything in real time applications vastly outnumbers the total, the total number of processors manufactured worldwide. So this is the regular processors, the non-real time processors. And so if you think about it, many of our appliances, be it a microwave machine, a washing machine, a dryer, anything, it does have a small processor which has to be a real time processor because it is dealing with physical stimuli. And I may still have only one computer in my house, but I'll have many of these gadgets. That is exactly why real time processors and real time computing is so important, even though we don't actually get to see it. So, why such a surge in embedded applications? Well, the surge is that, see, long back washing machines were mechanical, they did not have a lot of electronics. Or maybe they had simple circuits, but they definitely didn't have full scale processors with programming environments. Now they do because of the reduced cost. A lot of flexibility because of the internet, in the sense we have Amazon Alexa, which can control our lights, our fans, everything. And so that is there. Power consumption has reduced, size has reduced. And the most important aspect is that the processing power has increased substantially. And even the hardware, basic hardware software reliability has also increased to such an extent that these processors can now be used, right? So where are all the embedded systems here? You can see they're everywhere. Printers, airplanes, cars. In fact, a modern car has a lot of processors, right? Not a few, but it actually has lots and lot of processors for everything that we do. A lot of electronics in the car, all our safety systems, entertainment systems, everything. Video cameras, including coffee machines. So nowadays there are smart coffee machines. Toys for sure, phones, rockets, trains, radars, navigation systems, you name it. Everything has a small processor in it, which determines its behavior. So, what is real time? Real time is where there is a notion, a quantitative notion of time is there, which is measured using a physical clock. It's like a real world clock, and that determines the behavior of the system. An example, So let's say that the temperature, once it exceeds 500 degrees C, we do something, and the corresponding action is that some coolant needs to be sprayed, and that needs to happen within 100 milliseconds. So this is an example of a real-time constraint, and a processing system that implements this would be a real-time system. This is in contrast to the qualitative notion of time that we have in regular distributed systems. So there, of course, time is expressed using notions such as before, after, sometime, eventually, and so on. So the point there is that when we use before and after, so we typically use happens before and happens after relationships. So when we say that event A is, happens before event B with an edge of this kind, then it basically means that the time between them can be arbitrarily high, right? It doesn't matter. It can be very, very high. So embedded system applications, so they are there everywhere. Definitely in all of industry, we don't get to see that. So they are there in industries and factories. So one example would be a chemical plant control, where we have a large chemical plant and all the control circuitry over there would be an example of real-time systems. Automated car assembly. So in automated car assembly, the idea is that a regular assembly line for cars nowadays has manual workers, human workers, no doubt, but it also has a lot of robots who work in very close synchrony. So these are all examples of real-time constraints. You can just Google for an automated car assembly line. That's what it's called. And you can see you just count the sheer number of robots. Then, of course, we have SCADA systems. So they are using big systems like dams, furnaces, power plants, and so on. So it is nothing but a large network of these embedded real-time devices. So stands for Supervisory Control and Data Acquisition. So nowadays, advanced medical technologies, particularly telemedicine and remote surgery, are coming in. So that they use a lot of robotics, and also in some of these radioactive surgeries like gamma knife surgery and so on, a lot of robots are used because the environment is not very safe for human operators. So there again, the processes that are used will use real-time constraints. Then when we talk about peripherals, all peripherals are real-time: printers, cameras, camcorders, sensors. And definitely our cars. Our cars are the biggest example of real-time systems because earlier a car just was a mechanical object. So you just entered fuel into the engine, you pushed fuel in, and then the engine generated power. That's not the case anymore, in the sense that in modern cars, what really happens is we have a lot of electronics, and the entire process has a lot of fine control. So there is a multi-point fuel injection system which maximizes the mileage, minimizes vibration, and this is controlled with a lot of sensors and controllers. Again, a real-time system. Then our mobile phones, aircraft for sure, and this is a very safety critical system because nowadays modern aircrafts have the fly-by-wire concept. So with that, we have a lot of processors, and they obey real-time constraints. Internet, of course, multimedia applications. So now I'm recording this video at the time of a lockdown. So my life goes on via video conferencing, consumer electronics, cell phones, digital cameras, and definitely defense. Missiles, radars are big consumers of real-time systems. So if I were to look at a typical car, it's a slightly dated example, but modern examples of course, taken this far ahead. It'll have 100 processors per car. Modern cars will have many more. Depends on how you count, but definitely for engine control, the brakes, airbags, even small things like windshield wipers and so on are becoming smarter, and definitely door locks and entertainment systems as well. So this is all for a regular car where we have many of these processors. But the moment we bring in autonomous driving, the entire system changes because autonomous driving is as real time as it gets. So there are a lot of real time constraints which cannot be ignored. Otherwise, the car will have an accident or it'll stop. So that's the reason there's a massive amount of code also that goes in the modern automobile. So a BMW 7 Series car, which is written with an old Windows Mobile OS, has 2 million lines of code. It has over 60 microprocessors. 53 of them are really small 8-bit ones. 11 of them are 32-bit ones and 7 of them are 16-bit ones. And it also has multiple networks. So within a car, we also have a network of these devices. So it has multiple networks like a CAN bus or uh, there are other protocols like LIN and MOST and so on. So cars have these engine control units known as ECUs. They're also called electronic control units. Not that commonly, but some people do. And I myself am a subscriber of that abbreviation at least. So in this case, for each of the modules, there is a small processor. As you can see, airbag, body, driver door, cruise control, and so on. And all of them communicate, and needless to say, real-time constraints have to be followed. So an example over here, if you would see, this is a typical network diagram of a car network. So this is a CAN bus. So CAN bus is a controller area network. If you find that hard to remember, you can remember that as car area network, even though that's not correct. So then we have these buses that control, as you can see, the engine, suspension, brakes, and so on. So this is the main control line of the car. Then, of course, we have smaller control lines. So they control the wipers, lights, blinkers, and so on over here. And some of the key customers of real time technologies within a car would definitely be the fuel injection system because that determines the vibration and also the output of the engine to a large extent. Vibration meaning the engine vibration here. Cruise control, so where we basically tell the car that look, you need to maintain a certain speed, let's say 60 kilometers per hour. So in that case, if the car speeds up a little bit, then the rest of the car has to react and it needs to come down. Anti-locking brakes, airbags, keyless entries, climate control, GPS, they're all connected via this bus, and each one of them is a real time system. So, what we will study is how are these individual systems designed and how do they communicate over a network. So, coming to the multi point fuel injection system, what you can see is that this is a multi cylinder engine. So, fuel is being injected into the engine via an intake valve, and this is the airflow. So, air is coming in that way. So there are computers which are controlling how much fuel is injected. So that determines, of course, the output of the engine in the sense the torque it generates. And furthermore, you would like to balance it in such a way such that you generate the maximum possible power with the minimum possible fuel and also reduce the vibration because the vibration is a function of how much these pistons move. So that's the reason there's a need to receive the signals from various sensors, process them, and again send signal back to the actuators in the sense the actuators would control the amount of fuel. Cruise control, again, the same example that I was giving in the past to keep the speed of the vehicle constant. So let's say 60 kilometers per hour is the desired speed. So the frequency in which the computer will check the speed and then react is important. So what is important over here is the rate at which the computer checks the current speed of the vehicle, the rate at which it makes decisions, and then conveys the decisions to the actuators to correct whatever is the deviation in the speed. In a sense, if the speed is high, you reduce the speed by reducing the power that the engine generates, and vice versa. So, now let's discuss a reactive system. So, most of the time, real time systems are a part of reactive embedded systems where you read some inputs, which are also known as stimuli from the environment. You respond to them, which means if something changes in the environment, for example, if the car speeds up, you respond to it with an action. The action would be to reduce the speed of the car. So this would be a reactive system, and typically, when real world and real time constraints are involved, that would involve some of the concepts that we will study in later chapters. So let us start with the first list of concepts. So we can have three kinds of events. So they could be periodic, sporadic, and aperiodic. So periodic means that they happen, there's a fixed period to them. So an event happens sometime later, which is known as a period. Another event happens, then another event, and so on. So almost all activities in small systems are periodic because we periodically, let's say, sense the environment, and in response, something is done. So this is a periodic signal. Sporadic means where something occurs statistically or randomly, but there is still a little bit of an order in the sense there is typically a minimum separation between two events. So between two events, let's say that this is the separation. So this is there, right? If we don't have the minimum separation, let's say between event times t2 and t1 and t2, so t2 minus t1 is greater than some threshold. That's what means sporadic. And aperiodic basically means it is sporadic, but this threshold is zero, which means multiple events can occur together. So aperiodic is really random, which seldom happens in a real-time system, but we typically have periodic and sporadic events. But if let's say you want to make a very general system, then it needs to look at aperiodic events as well. How do you specify an embedded system? Well, we need to model all the events and actions. There could be complex systems that could have thousands of events and action types. So we need to divide it into subsystems and meaningfully model it. So look at a laser printer. So the way that a laser printer works is that we take an image, divide it into a matrix. So every row, if you consider a black and white laser printer, so every row can basically be thought of as a set of pixels, white pixels and black pixels. So this is known as a raster image, and this would be like a row of the raster image. So what the laser beam would do, from where the laser printer derives its name, is that it will neutralize the charge on the black parts of the image. So if these are the black parts of the image, it will neutralize the charge, and the white parts will remain charged. So this will of course generate a static electric negative image, mainly because what we want to print is not charged. And then of course we spray, these small droplets of paint, and then the paint essentially sticks to parts of the paper that have been neutralized before, right? Whose charge has been neutralized before. So otherwise they get kind of repelled. So that is how the image on the paper forms. So this, of course, is a real-time operation in the sense that the entire computation needs to be done before actually process the next line, because the paper is kind of moving. It's on a rotating spindle, right? So basically the paper is moving, but this entire computation, etc., needs to be done for one line before it actually comes. A mobile phone is like the king of real-time systems. So be it any kind of system, GSMA, CDMA, 3G, 4G, 5G, doesn't matter. There is a lot of communication that a mobile phone does. So that is why I refer to it as the ultimate lord of real-time systems. SCADA systems are used in very large systems, particularly dams, power plants. So there it's basically a large computer system which monitors and controls processes. A lot of sensors that store data in a real-time database which is distributed. So there are some supervisory system issues over here for controlling the entire thing. And this is again an example of a very large industrial scale distributed system, which is real time. And if you actually look at another very quintessential example of a real time system, that would actually be an aircraft. So the aircraft, many aircrafts nowadays fly in autopilot mode. So then there is a current position, XYZ, the velocity, of course, acceleration. So let's say we want to fly the aircraft towards a certain destination with a certain speed. So there are actually many of these actuators which get real-time data, compute what exactly should be the power that the engine should be creating. And so this entire process is kind of automated, computerized these days. And the deadlines may range from a few micro to a few milliseconds. So the deadlines are really small. Anti-missile systems, many of us have been following the news. So nowadays, many countries are acquiring anti-missile and anti-drone systems. So what happens is that if a missile is launched, it's going like this. So then the other country would launch another missile to kind of intercept it over here and essentially blow it to pieces. So what it needs to do is that its cameras need to continuously home into the missile. So it could be a visual camera or it could be capturing some other part of the spectrum. But once it has homed into the missile, it will lock on to the target, figure out its trajectory, find a place to impact, and then burst over there. So here the response times are very small, typically microseconds, if not less. And this is why this would also be an example of a very sophisticated real-time system. The key question: why implement an embedded system using a lot of software and hardware? Why not implement everything in hardware? Well, the reason is that hardware is inflexible, right? Hardware once designed is fixed. So the advantage of doing a lot in software is that it gives us the flexibility. Furthermore, there are many things which are very hard to do in hardware, right? With software, we can use advanced programming languages and data structures. So that is why embedded systems, by and large, other than the basic microcontroller, of course, is primarily a software artifact. So let us look at some important recent trends. So nowadays we have these smart TVs and video conferencing and so on, which for at least for me is a boon during the lockdown. So these are all examples of real-time systems where it is doing YouTube at the same time, it is getting feeds from the satellite at the same time. We still don't see any jitter. So another thing would be with modern embedded systems is that it is very easy to monitor and debug. There are typically web browsers, so we can go there, we can find out what's happening. So of course, these systems are getting much easier to write, program, and manage. But the key understanding is that we need to carefully co-design hardware and software, and we need to understand real-time fundamentals quite well, which this course is all about. So the basic model of an embedded system would be like this, that we have an input conditioning unit. So this is for basically the getting the event from the environment. From the input interface, we process the event, send it to a real-time computer. The real-time computer may additionally be connected with a human interface, doesn't matter. So it would compute the response. So it will compute the response of whatever the computer is trying to say and then pass it to the output interface, which is to the actual. So many other real-time systems are actually control systems where what comes in is an analog signal. It is converted to digital over here. We compute that what are we supposed to do with the actuator, in the sense how will we modify the actuator. Then the actuator is modified. So then we see, so that essentially changes some physical aspect of the plant, which is the system being controlled. Sensors pick that up and again they send the reference. Again, they send the values. So basically, we know the reference, we know what it is supposed to be, and this also captures the rest of the environment, which is not being modified. And we also get to see what exactly the sensors are capturing from the system that is being controlled. Based on that, our algorithm keeps computing newer and newer configurations of the actuator. And this is how we proceed. So, of course, the real time nature is there. We can see that. And the other thing is that decisions need to be taken quickly. Otherwise, the system may get uncontrollable, as we shall see. So, the pseudocode for this system would be to set a timer to interrupt periodically with a period t. So this would be an example of a periodic task. At each timer interrupt, well, we'll perform an analog to digital conversion, compute what is the control output, and convert it back right to the actuator so that the actuator can actually change the controlled system, some aspect of the controlled system. We can have multiple multi-rate control systems in the sense that many complicated control systems will have multiple sensors and actuators, like a helicopter, for instance. So the helicopter would have different tasks with different periods. For example, each 1 by 180th second we can validate sensor data, right? And every sixth cycle we can do a bunch of things with control. Every other cycle we can do something. So the key idea is that when you're looking at a very complicated system, we can have a bunch of periodic tasks with different periods for doing different things, as we can see in the case of a helicopter flight controller. Also, we can have hierarchical systems such as an air traffic flight control, where we'll have an interface or some kind of a system for the air traffic control. Then we can have something for the navigation, something for the air data. So these can all be connected. So this basically means that in any real-time system, if I were to model this, we can have a lot of tasks with their own interdependencies. So as you can see, the state estimation of, let's say, primarily the navigation module is being used for flight management over here. And this is providing an input to the flight control. And again, the state estimator is also providing an input to the flight control. So we can actually see a lot of things. So starting from the operator going downward, right? So basically where the sampling rates for the operator will be higher and the sampling rates for the aircraft will be much lower. What we can see is that one layer provides inputs to the other layer. And in a sense, the real-time tasks themselves are some kind of a dependency. In a sense, air traffic control provides its inputs to the flight management module, which provides its inputs to the flight controller module, which provides its input to the actual aircraft. Signal processing systems are, of course, required that convert from one format to the other, and response times can vary. Another such example would be a radar system whose job is to basically store digitized data in memory of whatever it is sensing, use digital signal processors to process it, and also have another data processor to process it. And finally, look at the records and basically keep showing the screen and basically identify friendly aircraft or enemy aircraft. Coming to sensors, well, a large number of different kinds of sensors are used in modern embedded real-time systems. So we could have photovoltaic cells to convert light into electrical energy, temperature sensors, pressure sensors, vibration sensors, acceleration sensors, all kinds of sensors are there. Sensors are typically low cost, as you can see from left to right. The IR sensors, then GPS, right? So this is a CMOS camera, right? An electronic compass. So we have, a large number of sensors are actually used. What is an actuator? Well, an actuator is the reverse of a sensor. In a sensor measures a physical input, converts it into an electrical signal, whereas the actuator takes in an electrical signal and converts that into something physical to change the environment. So the physical actions could be motion or a change of some kind of a thermal, electrical pneumatic, hydraulic, some property of the environment. So actuators are typically motors. So for example, in the case of a robot, to move its limbs and so on, they would be motors. But you could also have heaters or other hydraulic and pneumatic actuators in bigger robots. So a servo is another quintessential example of an actuator which is used in robots. It's a small device which has a shaft. So the shaft, the angle of the shaft is something that can be controlled, is something that can be programmed. So it can be positioned at different angles by sending a signal. So so you would typically hear of servo motors, which are essentially these motors which can be controlled with an electrical signal, and they are heavily used in robotics. So as long as the signal can be sent, the servo will maintain the angular position of the shaft, and if the signal changes, the angle changes. So this is very important in robots, of course, toys also, and also in radio controlled cars, again toys, but of course it is finding its way into other kinds of electronics as well. Signals, needless to say, those that come from sensors have to be conditioned in the sense that their voltage levels have to be changed, either shifted or amplified, because whatever voltage the sensor generates, that level of signaling, that level of the signal will actually not be good enough for processing in an embedded system. Then, of course, frequency range shifting that needs to be done. Signals need to be massaged in all kinds of ways. That is the key take home point of this slide. So, one thing we have continuously been seeing in a modern embedded system with sensors, that is, of course, real time, is that from analog world, we have an ADC, which is analog to digital converter. And then at the end of the actuator, we have a digital to analog converter, which converts digital signals into analog